What's up, guys? This is Carl Oliver and Austin bringing you a solution to the knapsack problem. Now, the knapsack problem is a question that asks, okay, how many different types of things can I fit into a backpack of finite size? Now, these things may take up different amounts of space, and they also may be valued at different amounts. So it's asking you, okay, how efficient can I be? What's my maximum? And given that I have to follow this weight, right? Now, the pseudocode that we're going to use for this project, for this solution to this problem, is as follows. We have two for loops, or a nested for loop, I should say, starting from j equal to 1 to n. Now, this corresponds to the different types of items. So, say for instance, j equal to 1, we're only worried about fitting A types of items, or items of type A, if you will. N equal to 2, we're worrying about fitting in items of type A and B. And then 3, ABC, 4, ABCD, so on and so forth. I'll portray that pictorially in just a moment. And this for loop corresponds to the backpack size, or the knapsack size, from I equal to 1 to m. Now, this may seem a little strange, but essentially what we're asking is, okay, how many things can I fit into backpacks of starting from size 1 all the way to some arbitrary maximum size? Now, what this if loop is doing right here is just essentially making it so that we don't really care about the problem when the backpack is big enough to accommodate any item. So like a backpack of size 1, we're not going to care about the problem if, you know, the lightest thing weighs 3. So obviously you can't fit 3 into 1. Now this portion of the if loop is essentially asking, okay, for my backpack of size, let's say 3, or I equal to 3. If I add an item, will it essentially increase my value, given that it's now big enough, like I said, to fit said item? If it is, you add it to the array, or you've put it into this backpack of size 3, right? So you're just adding in something that weighs 3, for example. And again, pictorially, just follow along, and I'll show you in just a second what I mean. And then we add that particular item that we added into this best array, right? And we're going to keep doing that. We're going to keep adding these items into these knapsacks. So again, the cost array corresponds to the knapsack. And the I is telling you, oh, how big is the knapsack? So essentially you have this array holding knapsacks of various sizes. Hopefully that clears up what it looks like. Now, for our problem, this is a pictorial representation of what I was talking about. But this is just some assumptions. We're going to assume that we're talking about 5 different types of items, so our n is going to be equal to 5, right? And these are their weights, or I guess their sizes. This one is 3 big, 4 big, 7, 8, or 7 big, 8 big, and 9 big. And we're interested in fitting these items of, you know, different sizes into different types of knapsacks, specifically in order from knapsack of size 1 to some arbitrary n. We're going to assume 17, but I'll show you what that looks like in just a moment as well. Now you notice that these 5 items have different values ascribed to them, and that's where our maximization comes in. Now we're going to be looking at a stack trace for these different types of items. And I want you guys to remember that, again, this is a very inductive, very logical sort of staircase problem that takes advantage of the facets of dynamic programming. Specifically, the fact that we have to save, I'll just show you that again, the fact that we have to save what we added, the best, you know, item that we can add to a knapsack that will give us the maximum value. The fact that we have to add that to an array takes advantage of the caveat of dynamic programming, where you don't have to calculate, you don't have to make this clunky calculation again. You can just go back right here, cost I minus size j. And that's very important, because right here, it's essentially asking you, right here in this little bit of code to the right of this statement, this is where you ask, okay, this is where you build up. You ask, I already filled a backpack of size, let's say, 0. Technically you didn't, but a backpack of size 0, that's where you start off. So you're adding a 3 to it, so that way next time you can say, oh, I already added something. I already know how many of a certain type of item can fit into a backpack of size 3. So that way, you already have that answer, and it builds up as you ask even bigger ones. And I'll show you what that means. I'll show you specifically what I mean in just a moment. Now, this stack trace shows essentially that entire pseudocode for j equal to 1 to j equal to 5. And again, j equal to 1 corresponding to items of type A, 2 items of type A and B, so 2 different types of items, 3 different types of items, 4 different types of items, and 5 different types of items. And this essentially this entire thing answers our question of, oh, we have 5 different types of items with their given properties, and we're going to end up with a best array in which we're going to take advantage of. This is what we're going to take advantage of in order to answer the question, oh, what's the subset of items that will give you the highest value that still meets the finite size limit of our knapsack. Now, as you can see, the stack trace is pretty simple for the items of type A. You just think, oh, okay. Again, we know that our little A's are worth 3. Excuse me, they're worth 4, but they're 3 big. So when the knapsack is able to hold 3, we just slide in an A in there. And now, oh, boom, this knapsack is worth 4 because it has an A in there. And then you just keep going along. Oh, 4, you can only put 1 A in. 5, you can only put 1 A in. Now, we get to the interesting part. We get to the part where we say, okay, our knapsack can now accommodate an additional item because we have a knapsack of type 6, or of size 6, and we are now actually able to insert another A because it's also 3 big, 3 plus 3 is 6, easy math. And as you can see, the cost of the knapsack is now 8, and our best array doesn't really look all that different because you're just saying, oh, okay, just add another A to that. And this is what answers your question. You asked, oh, what's the best thing to add to this knapsack that's 6 big? Well, you're answering it here. You're saying you're going to add A to this knapsack of size 6, which is also essentially comprised of knapsack of type 3. So you're saying that's where the induction comes in, right? We say, oh, we answer the question of knapsack of size 3. So that essentially comprises that part, the efficient part right here, comprises what knapsack of size 6. That will maximize it. And essentially just keep going. Oh, 9 can now accommodate 3. Obviously, A is the best thing you can add here. So now it's worth 12. So on and so forth until you add another one, and then you add a 20. Now, when you add another type of item, which would be the A's and the B's, it gets a little different, right? You say, oh, okay, boom. Knapsack of size 3 can accommodate something as big as 3. But now, knapsack of size 4 can actually accommodate B now because it's, again, worth 4, right? And now you can say, okay, well, it's better for me to just add a B, right? You don't need to, you're asking, oh, okay, you just add a B and then you're done. And then you take a look at your 5, or knapsack of size 5, I should say, and oh, it's still the best answer is B. That's what will maximize my, my take for knapsack of size 5. Then you get to 6, and you already know, oh, well, you already answered that over here, right? You said if the best answer to this, to my 6, is just going to be whatever I added previously. So I have a 4 here. I can accommodate something of 3. The only thing I can add to it is an A. Boom, done. But then now you can accommodate 7. In which case, oh, well, I added a 4 previously here, and now I can add a 5. Excuse me, I can add a 4. And 5, which is what B is worth. 5, the value of 5 plus the value of 4 is equal to 9. And then now your knapsack is worth 9. And essentially you keep doing this. You keep following this chain of, oh, what can I add to this knapsack that will still be under this weight limit that will make it most efficient? And that's what this best array represents, right? This is where you store that information. This is where your dynamic programming comes in, right? And at the end, after we trace the entire algorithm, and we can now answer the question, oh, given these 5 different types of items and the properties that they hold, what is the max? Not only what is the maximum value, which would be 24, this is only for a knapsack of size 17. That's an important assumption that we have to remember. And given these properties, the highest I can ever get with 5 different types of items is 24. And I'm going to show you what subset of items can help you do that based off of this best array. Now, remember how I said, I keep emphasizing this fact that, oh, you're essentially just answering this question inductively, right? You're saying, okay, given my knapsack of size 17, right, and given these 5 different types of problems, the answer to the question of, oh, what's the best combination of items? It's simply just other combinations of other items that are also made to be efficient. So if you made your base efficient, and the next thing that builds off of that will also be efficient, so on and so forth until you follow this inductive reasoning, and then you logically have something that will maximize your value based off of your limits. Now, right here we have our example of size 17. If you take advantage of the fact that the best array has everything you need, like it says, oh, what's the best thing to add to an array of size 10, an array of size 3, you get, boom, this knapsack of size 17 will have a maximum, and a most maximum in which it will satisfy these limits. The subset of items will be CCA, because you already asked what's the best for a knapsack of size 3, what's the best for a knapsack of size 10, and knapsack of size 17.